Hello classmates, Tim Outland here again, assignment 6, informative speech. What follows will serve as the background for my final speech, week 8, persuasive speech. I will be introducing solar power concepts in this presentation. I've referenced several sources: Wikipedia, U.S. Energy Information Administration, HowStuffWorks.com, DIY.com, MichaelBlueJay.com, KOA RV Services, and my own personal experiences building and maintaining my own solar power system set up at my hunting camp. Solar cells, PVs, photovoltaics are not new. The first PV experiments go back to the mid-1800s with the first successful PV experiment created by Mr. Charles Fritz in 1883. And while that first cell was only 1% efficient, it was the start of the PV energy quest we find ourselves at today. PV research struggled for years with different scientists, engineers, and nations working on a better way to harness energy from the sun. It was not until the 1950s that efficiencies achieved 6%. It took the space race to advance to the next level, with solar power being effectively captured, created, and stored as energy from the sun. Basically, PVs turn absorbed sunlight or other artificial light into electricity by interacting of two different materials used in the cell, chemically reacting with each other, producing an electric charge in response to light exposure. A simple setup: sun coming through, material A, material B, the two work against each other, create the electrical output voltage that we need for solar power. There are 4 types of solar cells in use today. The least expensive to produce are the amorphous cell, a non-crystalline type of cell, low efficiency of less than 10%. Commonly used for things like calculator power, watches with dual power, and low-end battery chargers like you might plug into your cigarette lighter and lay on the dash and keep a trickle charge going to your car battery. Next would be the polycrystalline cell, more commonly known as thin film. It's a little more expensive to produce, better power producer, uses a copper base or cadmium based elements in its structure for efficiencies of 10%. The monocrystalline cell is the standard cell most of us are familiar with. You may have seen these before in catalogs. They use pure silicon material for 15 to 20% efficiencies, or gallium arsenide material for up to 25% efficiencies. Unfortunately, as the purity of material and efficiency goes up, so does individual PV cost. The last cell to talk about briefly, the newest technology, still in development, not really commercially viable at this point for mass power production. It's the next wave in solar energy, hoping to achieve to 30 to 45% efficiency. Throughout this presentation, I'll refer mostly to the monocrystal photovoltaic going forward. As before, here's a panel. This is an 80-watt panel, basically capable of producing 80 watts of power on a full sun day with a charge current of 4.5 amps in full sun. And as you look closer, you zero in, there's a bunch of little squares there. Those are individual PV panels. Each one of those PV panels or cells is capable on its own of only producing 1/2 a volt of electricity at 1/10 of an amp of charging current. The individual cells are wired together in series and also in parallel to give you the amount of voltage and current you need for efficient solar power production. Expanding further, needing more power for keeping up with your power demand, individual power panels are ganged together in both groups in series and parallel as the power requirement dictates. Typical panels one would see in a residential setting are sized 44 by 24 inches or so individually, or a whole house rooftop unit requiring approximately 120 square feet of space, or an 11 by 11 footprint. You've seen pictures of whole house solar systems before. This is about what it looks like. 15 80-watt panels for approximately 120 square feet should produce a generation on average of 1,300 kilowatt hours per year of electricity, depending upon how much sun exposure the panel sees. According to the U.S. Energy Information Agency, the typical U.S. home in 2012 used 11,000 kilowatt hours per year of electricity, depending upon how much sun exposure they saw. Also depending on the region. In Louisiana, it's not uncommon to see a 15,000 watt consumption with its hot summers, compared to Maine with only 9,000 kilowatt hours with their climate. From these numbers, one can see the average solar augmentation routine. There's a 9,700 kilowatt deficit, requiring additional power generation technologies, be it a larger solar array, reducing one's own power consumption, making up for the deficit, or staying tied to the grid. Some examples of how much individual powers consume. Let's take a device, run it 24/7, 730 hours in a 31-day month, and see how much power is used when you plug it in, turn it on, or flip the switch. Your common single 100-watt table lamp is using 730 hours in a month, would be a 73 kilowatt hour usage. Not so bad. Now multiply that 12 months for the full year, constantly on. Your light would now be using 876 kilowatts of that 11,000 kilowatt hours that we cited earlier. A small house air conditioner, say a 2.5 ton, uses 2,600 kilowatts per month in a 24/7 operation. 48-inch ceiling fan, a little bit better, it's not as cool, runs 56 kilowatt hours per month. Hot water heater, 27 kilowatt hours per month. Laptop computer, 33 kilowatt hours per month. A desktop 17-inch with a monitor, 67 kilowatt hours per month. Need a little entertainment and love the sports? Got to have that 50-inch plasma. Well, that's going to run you 253 kilowatt hours a month. Add in the Xbox for a little more fun, another 138 kilowatt hours. My personal faux pas, I like coffee. Coffee, 670 kilowatt hours a month. This is just a small sampling of where the power goes, and while nobody runs an individual device 24/7 for the numbers above, cumulatively together we can see a similar power usage in our homes in a given month. So now back to our solar power augment system. We see the kind of power we need day over day, month over month, but also missing from the story is the fact that all of the devices above, for the most part, run off of AC power. Guess what? Solar panels make DC power. That has to be converted to AC power. Or you have to get rid of all your AC power devices for ones that run either on dual power or DC power devices only. Darn, those aren't plentiful, efficient, and they're not very inexpensive. So we need another device, an inverter that changes DC to AC, either as a microinverter or a large whole house inverter. So now we have our whole panel set up, or series of panels sized enough, we hope, to at least give us some help with our electrical bill. Well, what do you do if you don't have any sun? You either must draw from the grid as normal, or literally and figuratively save it for a rainy day in storage batteries. Batteries work with your inverter to give you stored reserve power for when the panels are not being charged or there isn't any sun. Batteries come in different materials and sizes, but more importantly in a solar power routine are the amp hour ratings of your battery bank, or how long can the battery bank continue to supply the power before being depleted. Amp hour is basically calculated for a given load expected in amperage versus the ability over time for the battery to carry the load. In solar systems, we want to size so that what we take from the batteries when not charging can be made up by the panels themselves during the day. Much like we look at kilowatt hours produced used, we also look at average amperage consumed when running, so the system is properly sized for a balance. A typical window unit AC draws 12 to 16 amps, a computer 5 to 8 amps, a TV 1.5 to 4 amps, a washer dryer 14 to 16 amps. Then the individual inverter itself, converting DC to AC, either in standby or in operational mode, can run anywhere from 1 to 8 amps, waiting for the AC power request. This presentation was intended to provide you with some information missing when discussing alternative energy options, to allow you to make a more informed decision to see if solar works for you. Solar power is at present still a rather costly solution, but improving over time as technology also improves. It also holds great promise as a part of the solutions that we face day to day to meet our ever increasing energy demands. There's still more work to be required for viable energy solutions today, but this is just one look at it. Thank you very much.